and that way we can retrain the algorithm to better learn and detect cracks. And since we have to save the images and have experts to look at this, we also have to ensure the privacy of everyone. So we also integrate a blurring face algorithm to our solution. That's it. So here we have an example. So what we do is just send one image per one image at each breakpoints, but our solution also works real time, so that we don't want to overflow the experts with too many information. So I think I'm done for the presentation. Okay.
So what we have is a short video here that actually just shows all of this end to end, just to give kind of a more overarching story arc. We port to Hamburg, focusing on one particular site called the Harbour Block. And this is footage that we recorded during the test event in September. And we'll speak a little bit more later about how we managed to integrate the USV with the drones. But from the data collection perspective, this is the first round mission. It's effectively what we call a lawnmower style survey. It's straight and level parallel lines back and forth to establish the situation on the ground, so that then we can reconstruct and plan the close-in waypoints for the high-resolution photogrammetry and crack detection. Drone completes its survey, has about 35 minutes endurance, lands, is recovered into a cradle, and what actually happens here is the batteries are swapped out. In the meantime, the reconstruction and the second stage mission plan is created automatically without human involvement, and then we get this quite complex mission plan which surveys everything in detail. Something I'll talk about next, but we also monitor in real time as we're doing the survey all the air-to-air and air-to-ground collision risks, and we have mitigation systems in place in the event that we lose GPS, in the event that we lose comms. And then we have the stage 3, high resolution crack detection. This is what the imagery looks like when it comes out the other side. That's 1 mil ground sample density. And the drone can stay on site as long as it needs to. Because we have a 3-minute hot swap capability, so we're not waiting for the batteries to recharge, we're swapping in a fully recharged set. So the duty cycle of the survey is actually quite high. We're getting 35 minutes of flight for every 3-minute hot swap. And it's quite a fast automated landing and takeoff procedure as well. The USV gives the capability to ferry the drones from site to site, far beyond the flight endurance of the drone, which is the main purpose of it, and provide the remote energy management and mission support in the site. So that whole process, the USV entering the port, the multiple surveys, the crack detection and the photogrammetry generation is all fully automated without human intervention, and then the USV and the drone can leave the scene. Any questions at this stage? One of the things that this does is it opens up a plethora of issues around risk mitigation. The purpose of the pilot in a drone operation, the data collection is secondary. The primary is safety. These missions can execute with a pilot in the loop. The pilot doesn't need to have any intervention on the controls. Everything can be pre-planned, generated automatically on the fly. However, we do run the risk of having an incursion from, for example, a helicopter or a low-flying Cessna. or people entering the site. Without having a pilot or a spotter in the operating theatre, the drone is at the mercy of external factors. So we need to incorporate this into our risk management, and we need to develop a comprehensive safety portfolio where we have operational safety objectives. And these operational safety objectives are focused on mitigating the risk of air-to-air and air-to-ground collision, because we need to be able to replace the pilot and the pilot capability of taking physical and cognitive control of the drone in response to an emergency situation, in particular an incursion. Just a small bit about us, just for a little bit of background context. The collection of projects that we have in the University of the West of Scotland involving drones, we have typically found ourselves in maritime, agricultural and industrial use settings. The reason being, these use domains are the ones that can exploit the value of drones because they're sparsely populated theatres, and it means we can get approval to fly missions far more readily than we would in urban situations. So we develop embedded AI that we deploy on drones so that they can be operated in those use cases where they bring value. We, along with a number of our partners, operate out of an airfield. So we are used to working and dealing with recreational air traffic control. Our colleagues, University of Limerick, they operate out of Newcastle Aerodrome. And of course in the Port of Hamburg, we have the additional engagements with harbour masters, city authorities, air traffic control, and so on. We're familiar with this site. Our colleagues in Limerick are familiar with this site. So when we go to test there, they're able to help us with the risk assessments. They know the situation on the ground, they know the air traffic patterns, they know the potential risks and hazards. Our colleagues in Hamburg Port, likewise. We are now starting to find ourselves going out into sites, though, that are unfamiliar to us. And this is where we're having to build out our risk assessment capability, going into unknown theatres, being able to identify the hazards and develop the technologies that can mitigate against them. This is an established technique. It's called the Specific Operational Risk Assessment. It is defined by EASA. It's similar to a predefined risk assessment. And what we do is we consider it across two dedicated strands. The first is strategic. What we can establish pre-mission. Using maps, all available data, where we can identify the hazards and put in place the mitigations for air-to-air and air-to-ground. On the air-to-air, obviously we establish the risk in terms of the surrounding airspace, in particular if we're operating near an airport. We have developed a digital twin infrastructure where we can test both the drone perception and the human pilot perception as well, because there are considerations for visual line of sight. In the air-to-ground, what we saw earlier, the adaptive mission planning and the photogrammetry, that is the sole purpose of that. It is to be able to collect high-resolution photogrammetry data without incurring the risk of an air-to-ground collision. That incorporates trajectory-based deconfliction. We have multiple drones in the air, we can separate them spatially. So we know in advance that they shouldn't reach on a conflicting path. We separate out return to home points and containment areas and so on. With the best will in the world, we are still going to encounter unscheduled, unpredictable hazards during the mission. And we need to be able to detect and respond to these in real time. These are typically uncooperative incursions, for example, helicopters and planes that do not carry transponders. Recreational and small Cessnas and so on typically don't record their position. Military helicopters don't, they fly low and fast. We also, because we're working in and around transport infrastructure, these are big assets, we frequently encounter degradation of satellite navigation because of occlusion and multipath, and issues with communications. We can enter into dead zones and blind spots. So what we have put in place is a collection of mitigating technologies that are based on LiDAR, radar, and thermal sense and detect. So this is real-time artificial intelligence that we embed on the drone to monitor the surrounding airspace, to be able to detect incursions from helicopters, from light aircraft, and other drones. And we also have, for example, the stereo disparity mapping that we saw in the earlier video, where we can get the depth or the range to small hazards like the lamppost we saw in that scene, and simultaneous localizing and mapping, so that if the GPS falls out, we can still gain a positional estimation using, for example, the camera or the LiDAR data. I won't show the video again. The first step to this was to digitalize the SORA, and this is sped up just so that we can see it in the span of 30 seconds, but this is the typical SORA application. And basically, we categorize all the ground risk, the safety barriers, everything we can quantify and qualify about the operating theatre that we're going to operate in. And this gives us a digitalized SORA. From there, this helps to define the requirements for the detected divide. So what we have here is we have a helicopter. That helicopter can be detected with a thermal camera coupled with machine learning and some standard or traditional computer vision algorithms like dense optical flow, can be detected out to 3 kilometers. And what this does is it gives us time to react, because helicopters are fast moving. Our colleagues in the University of Limerick developed this and tested it out of Newcastle Airfield on the east coast of Ireland. The workflow basically consisted of hiring a helicopter, putting a GPS recorder on it, and having it run a series of incursion lines so that we built up a training data set. And then having it run another set of incursion lines and testing it with the drone in the air to see what it detect and track. So we established a 3 kilometer perimeter, and it's sophisticated. It's not just anything in the air as a helicopter. It is able to distinguish between birds, ships, helicopters. It grows as the training data set grows. And what this allows us to do is to detect and track incursions from uncooperative helicopters and light aircraft where we wouldn't know their position because they're not appearing on any ADS-B maps. Because we operate within an airfield, one of the things that always concerns us is being able to monitor the runway for the light aircraft and the gliders. This is at Stratham Airfield in Scotland. To be able to monitor the runway activity so that we know when a plane is about to take off. This is a flying school, and the students don't always follow the lines that they should, so we need to be absolutely aware of them, in particular when they're about to take off. So this is a radar-based solution. Because it's radar, it's quite high frequency. We can see out to maybe about 500-600 meters, but that is sufficient to cover the airfield from the site that we operate the drones from. And this is a PineNet based model, so it deals with the raw pine cloud data, and it is able to segment the individual pines into different class of object. For example, the ground, different categories of drones, some of the airfield infrastructure like the windsock, it can correctly segment that, and the hangars and so on. We worked with a company called Codeplay, who are an Intel subsidiary. They've developed what's called Sickle. It's basically a parallel programming language. And because we were able to work with them, they were able to modify their back-end software to accelerate the model. So we got them to focus in on 6 different operators around matrix multiplications and batch pooling and things like that. And we were able to accelerate the model somewhere between 4 and 6-fold, depending on the type of data that comes through the model. So what we have is we have a real-time system that is able to segment radar data to, again, fill in the picture of the airspace risk. This is an automotive radar. So this would typically be at the front of a car for your adaptive cruise control. They don't make sensors for detecting and avoid from drones because there is no use case where they're needed, because beyond visual line of sight isn't typically permitted. So what we're always doing with these sensors is we're taking survey sensors or sensors from other domains and having to repurpose them. That's not always easy because stuff that's designed for cars doesn't have the same size, weight and power constraints. We have a payload capacity of 2.7 kilos on this. Some of these sensors are in excess of a kilo. The embedded compute with the housings and the mountings and the cables can grow to 600, 700, 800 grams. We put some Wi-Fi on it. We get very close to that 2.7 kilos. We can draw 96 watts off the drone power supply. The drone itself has an overall energy budget of 550 watts. And for the most part, we try and have the system vendor agnostic. So it's basically mounted on the drone, directly connected to the sensor. And in some cases, we've had to buy the constituent parts of the sensor to be able to get access to the real-time data, because DJI do vendor lock, and they don't always give you access to the raw data. But typically, their sensors are repackaging of other companies. So for example, their L1 LiDAR is a repackaging of a Lightbox Avia, except they add an IMU and a stabilized gimbal and so on. One of the things that we were encountering when we were creating training data sets for the artificial intelligence was when you want to create AI to detect safety critical scenarios, to build that training data set, you have to put drones in safety critical scenarios, and you don't always want to do that. So one of the things we did, in particular for the LiDAR work, is we built out a full simulation model. And we built out a simulation model that took into account the fact that these sensors, they're not like cameras, they're not single shot. They build up the coverage over about 0.8 of a second. And it's basically, these are spinning prisms. It's like a spinning flower pattern. They have a very non-uniform resolution, both spatially and temporally. You have to take this into account because objects will appear differently, and they'll have different levels of sparsity and different sampling distortion depending on where they are in the field of view. So we built out a full simulation model, and what it allowed us to do was we could take real data from instances that were low risk, and we could insert synthetic data into those data sets of high risk encounters, like two drones getting too close to each other. Then what we did was we took an AI model that had been trained for automotive, it's called point pillars, and we deployed it on a drone, and we deployed that drone in a sentry role where its job was to observe and monitor the other drones in the swarm. Because we found that when we were serving in situations like the lock, we started to lose accuracy on the GPS. All of a sudden our error started to grow by a few meters. Now if we're surveying and we're bringing a drone to within 3-4 meters of a concrete wall, but we're bringing two drones to within, say, 10 meters of each other, if both of those drones start to drift by a couple of meters, we are going to cross a separation threshold. So what we did was we trained the model with both real and synthetic data, and we benchmarked it against models that were trained with real data alone, and we outperformed them. And the objective here was to be able to monitor the separation distance between the two drones. And we could do this relatively, this did not have to be in an absolute coordinate system. All we needed to do was to be able to measure the separation distance between them, and if they got closer than, for example, 10 meters, we raised an alert. This graph here just shows the separation distance between the drones that we were tracking, and through a combination of the point pillars, detection algorithm, and a tracker that we developed, we were able to maintain a consistent lock on both drones. And the positioning here is significant because there's one drone quite low down and in very close proximity to the concrete wall. We're only picking up about 2 to 3 points per second for that drone. It's very sparsely defined. The other drone is quite high, and it's, you know, there's a clear volume around it. Its backdrop is trees and other things. They're two very different kind of contexts, so it is quite a challenge for an AI model to be able to track both of those. And that was why we kind of set it up in that way. Okay, let's start bringing this to a close. The digital twin. So obviously some of these test sites, we were only getting out to them maybe once a year. So what we started to do was we started to sit, the reason this is a double image, by the way, is it's a virtual reality headset display. So what we started to do was we virtualized the scenes, we virtualized the mission plans so that we could actually understand and train ourselves in terms of how long these missions are going to take, what does the risk situation look like. We did find ourselves in situations on occasion where within visual line of sight, we found ourselves in a very challenging environment. So for example, one of the surveys we did here of the name of the bridge escapes me. Anyway, it's not on the image. We deployed from a pontoon, so two pilots, one pilot and a spotter on the pontoon. But to cover the full span of the bridge, we had to go out to about 500 meters. And we were surveying at, I think, about 140 meters high. Because the bridge height was over the 120, but we had permission to go out over the top of it. In Hamburg on the River Elbe, you're not allowed to fly over boats. So when a boat would approach, we have to make a decision: do we stay on the far side of the bank, this is down to battery basically, or should we recover to the near side and let the vessel pass? One of the things you can see on that stretch of river, it is very busy. There was a boat passing every few minutes. And what we found was it was actually quite challenging, because it was a rainy day and there was a smokestack in the background and all the rest, to be able to rapidly take physical and cognitive control of the drone, get the orientations and bring it back. Because for some reason that absolutely escapes me, these drones are always dark grey. They are practically invisible against a dark grey sky. So we started to, when we came back from Hamburg that time, we actually recreated this scene in the virtual reality environment, because what we wanted to study, and it's a PhD student who's working on this, is the human factors that actually need to be incorporated into the risk assessment, not just the technical factors. That even though we may be within the regulations, we still need to assess the environment, the weather, the direction of the sun, and so on, because it's not always a given that even within 500-600 meters you'll be able to maintain a visual lock. So what we've started experimenting with is different colors. Can we establish a higher contrast? Most of our consortium come from a marine background, where when we go out there, all the AUVs and ROVs, they're all either bright yellow or red. So it's why these are always camouflaged. I guess is that they're military underpinnings. But we started to investigate what can we do to mitigate the risk here. Where are the circumstances where we need to have a visual spotter involved, and so on. So this is the kind of the virtualizing the cost and the risk. So across all of these, the strategic and the tactical, air-to-air and air-to-ground, we have developed a collection of technologies that support the data acquisition. And while the data acquisition and the processing now no longer requires the human involvement, we are many steps along the journey as well in terms of replacing the pilot for the safety aspect. And the two go hand in hand. And we can't deploy these systems beyond visual line of sight in an autonomous or residential mode of deployment until we fully address all the safety aspects. And that's what we focus very heavily on in this project. And I'll take any questions on that if there are any.
Well, I would have one. So, in the world of autonomous vehicles, you oftentimes have this condition that you need a remote operator for those cases where the system itself cannot handle the situation. So, would that also be something that could be useful for the drone operation, that you have all those systems on board that you have described, plus you will have at least one operator for dozens of drones who can intervene in case of emergency?
Yes, the objective here is to get from a situation where we're human in the loop to human on the loop. And the human on the loop can monitor multiple drones simultaneously. They just need to intervene when there's an alert. That's not always that easy because you have to gain physical and cognitive control of the drone and the situation. But with explainability and so on coming more and more into AI as a mandated requirement by the regulators, these technologies can be brought together to very quickly explain the risk profile and very quickly make a recommendation and explain how it's making that recommendation in terms of the decision making. So yeah, that is the next step.
And right now, do you have 5G capability on board, or is that still in the future?
These systems are not 5G capable, but what we would typically use is we'd use a Starlink system. So we have our own Wi-Fi network in the field, and then we have a Starlink back to support servers, for example, for data offloading and things like that. That will give us 70, 80 megabit download capacity, so it's sufficient for what we need.
I'm just curious. I'm from Slovenia Railways. Just curious, would be that technology also suitable for railway observation, monitoring, let's say for the specifically for catenary lines, or maybe for tracks cracks? Because here are two specifics. Also less than millimeter cracks can be crucial here, and also there are also longer distances. How is the autonomy of that? So I'm just curious, how is that technology prepared, for example, for that
The
time?
safety methodology is domain agnostic. The maintenance inspection aspect, if there is a data set that can be annotated and we're still using supervised learning, then we can train those models. They are, for the most part, pre-existing models. There are things like YOLO. They've been around in AI terms. They're considered classical because they're 3 or 4 years old. But they're there. They exist. They can be trained to detect other features once you have the data set. More sophisticated models will segment. They will annotate individual pixels, so it's not just a box that we draw on the feature, but we can actually fill in the exact feature itself. Rail inspection is definitely one of the key use cases for this, and we do get approached by rail operators to see where we're at with this. They're currently using helicopters, quite sophisticated. 10 cameras on an array because they can lift that capacity and they have this insanely complex photogrammetry data set. But yeah, I think leaving these in residence with drone in a box solutions certainly opens up that side of things. One of our partner projects in Drones for Safety, their use case was rail inspection, and the way they dealt with the energy management was they would recharge off the power lines. So based on when a train was approaching, the current would flow in the line and they were able to recharge the battery. So there are quite sophisticated projects underway in that domain. Okay, if there are no further questions, I will hand over to my colleague Matteo Santos from the University of Limerick, who will talk about the integration between the drone and the USB, and the challenges and the solutions that we came up with there. So you could go with it. Yeah. All right.
Right, as James mentioned, my name is Matteo Santos. I am a PhD student at the University of Limerick, and one of the things we developed in Rapid was the extended area of operations. So, a few of our use cases in Rapid, we have shipload inspections, infrastructure inspection, emission monitoring, and fast response to events. So, what we want with this extended time is that we could cover a bigger area with our drone, because as James mentioned, we could have 35 minutes or up to 45 minutes with the drone, But if we merge the capability of the drone that can have fast access to the infrastructure, can carry multiple payloads like different sensors. So here we have a camera, but we can have a sensor for like a gas or LiDAR, depending on your application. It's compact and easily deployable, but we have a high energy demand and approximately 45 minutes flight max, usually 35 for safety, but we can go up to 45. But it's difficult to inspect like distance objects. So to increase that capacity, we can use our drone, the M300, along with another vehicle like the X-Ocean USV here. So we have a picture here of the port of Hamburg. So now with this vehicle, we can just go around this port and then just do the inspection of the desired area with the drone. So you can cover a bigger area because the USV can stay longer than 35 minutes, and then just deploy the drone at the area of interest and then do the inspection of that area. So now we are fusing the capabilities of the ASV that can carry high payloads. The majority part of the suit is accessible by water, so you can just go around with the ASV and you have long mission endurance with that. And we have merged that with the UAS capabilities. There's fast access, can carry multiple sensors, and it's compact and easily deployable. So with a drone, we can cover a maximum area of 9.8 kilometers with this 35 or up to 45 minutes flight. That area should be enough to cover the Rotterdam port or the Hamburg port. However, when we're doing inspection, this area is a little bit less because you need to stop and look closely to your infrastructure. So you could cover 2.6 kilometers with the drone itself. But when we look like to bigger ports like the Shanghai port, it's even worse because it's a really big port and we wouldn't be able to cover it with the drone. So what we could do here is extending our flight considerations. We now propose a solution where we have an automated landing system, a battery hot swap system, and the energy digital twin that I'm going to show you here. So when we merge the UAS with the USV, we are putting these markers on our USV. So when the drone finishes its mission, it's just returned to its GPS position, lands on the ASV, and then the hot swap will happen. Here we can have that was one of our early tests. So we were in Wicklow. That's our area for takeoff and landing. Here we are simulating where we would do our inspection. Once we're done, we return to that GPS position. We're gonna have an error associated with it because you are on an AESB probably, so it's not like really precise. When you get there, you go back to the camera sensor, and now you have a completely landing based on the visions. So you here have an example of the drone coming back after the mission to the GPS position. You can see that's a bit off center, and then right now we just switched for the visual controller. The visual controller will bring the drone back, and then we're going to do the landing on the marker. So you saw that on the video that he showed as well. So a couple of landing on the ASB itself. So right now we're just early tasks. So at this point we had a lot of measurement, a lot of safety added to the system. So we are trying to be really centered, you know, and then like every step you have like a hover. So the drone stops and hold that position to make sure that's fine, and then it keeps going. So at early stage, we're very concerned on keeping it safe and make sure that's going down. But then later we saw that on a real situation, you need to be fast to complete the landing. Otherwise, the ship could just move and then you just lose your position to land. So we removed all this safety that you can see there. So like as we're going close, we're just like holding position, make sure it's fine to approach correctly. But later we just saw that there's no use for that. The better is just like go as fast as you can. So because the ship is usually moving, like it's on the water, so you cannot be so precise because at some point the ship will move. So we complete the landing there. Here is just an example that we did on the first campaign of tests in Hamburg. So the drone again, it was just landing on the prototype of the of the ASP. It's still not the final landing. We still had the last hover on the last 2 meters, but we removed that again in the end because we just perceived that adds a bit of danger stopping too close to the ASP. But usually, well, for the last landings, we just remove all the safeties and the drone goes straight down in about 10 seconds. Once the drone is landing, now here you have a prototype of the hot swap. So the hot swap now comes out, catch the drone, bring the drone back, and now we're gonna change the batteries, and the drone has 35 more minutes to inspect another area of the port or the bridge or any other application that we need. When the drone is back, we have here a concept of the hot swap system. So the drone goes back in, you can remove one of the batteries of the drone. The DJI drone, if you remove only one of the batteries, it doesn't turn off. That's why it allows the hot swap. So the other battery goes in, now we remove the other battery, complete the hot swap, and the drone is ready to go without turning off. So we can do that again and again and again. So if we have a charging station for, like we usually have 4 sets of batteries. So that would give us like 2.5 hours of flight, and we can keep charging those batteries. So as long as the ASP can stay on the water, we can keep deploying our solution. So here was one of the early tasks. This was realized by CML, one of our partners on the group. So it was one of their first prototypes. So they tested that on the compliance. So here is a video after the landing. So we can see the system going out. We catch the drone. Yeah, align the drone first. And this was done up to 20 to 30 seconds. That would be fast enough that we could secure the drone. During that 10 to 20 seconds could be, the drone is kind of the drone could fall, you know. That's the only concern that we had at some point. But it's really fast, 10 seconds usually is not a concern for us. Okay, so the last here is the final model that they developed. So right now they just changed the motors for IP65 motor, 65 rated motors, so it could go on the water, and the battery swap could go here. It's just the final model that they designed. At last, we have here the energy digital twin. So these are the solar panels, and the solar panels would suffer efficiency loss under shading. Okay, so one solution is to use power electronics to mitigate the shading effect. And this LPE was system provided by DIG. So what we could have is just, you see the other structures on the ASP, we just block the sun, and that would affect the amount of energy that we could get from the solar panel. And then based on that, it was developed during Rapid, these solutions that could help to avoid this shading effect. And for that, we used the PV Sol simulations, and this was allowed us to reproduce these electrical layouts, and with that, the simulation is helpful because in energy system design and process optimization, and the software is used to assess the solar system retrofit by adjusting optimizers. And by using that simulation, we can increase the energy generation by 36%. So by using the MATLAB simulator, so here we can create the model that we are supposed to have on the ship itself, and by using this Simulink model, you can test the shading effect, and by that they can improve the energy creation by 35%. And with that last solution, the digital twin model predicts the power consumption of the DSP, and this is used to predict flight return times for the UAV that optimize its energy system. So the idea is that now you can have more time on site So charging the batteries with the solar panels, you can not use only the 4 sets, but charging those 4 sets and keep more time, increasing the time that you can do things. Okay? So the last here will be video, but James already played the video, so I'm just gonna skip it. Thank you very much. Any questions? James.
Thank you, Matthias. One of the key things that we wanted to achieve as part of the solution was a green survey solution. So that was why the USV that we picked, it's a solar powered one. Now it has a diesel generator as a backup, but it can operate fully under solar. Obviously sticking a large gantry on top of it for a landing and takeoff pad was going to eat into some of that energy budget and that solar harvesting capability. So that's where the line of work around the power electronics to harvest or to optimize the energy generation, but also the bifacial, because we're operating on water. The sun shines on top, but it also reflects off the water, so we're able to get a secondary return off the sun. There are also other considerations. I mean, the orientation of the USV relative to the sun, it can be controlled and it can have a significant impact on the energy generation. The full system, as far as the drone is concerned, it's powered off solar energy. And it's powered with, as Matthias said, it's a very fast procedure for landing. It's a 3-minute battery hot swap, and then it's away again. So the downtime during the survey is minimal. You know, it's maybe less than 10% of the overall, you know, flight profile. Drone in a box solutions don't typically do this. They may have a magnetic power connector, or they may be feeding from a hot plate up through the legs into one of the connectors. You're sitting there for 55 minutes waiting for the batteries to recharge. So the hot swap allows one to take one battery out, replace it, take the other battery out, replace it, 3 minutes, but the drone doesn't need to power down. The benefit there is you don't need to go through all the recalibration procedures for the IMU. You're straight back into the mission, and you can resume exactly at the drop-off point where it did the return to home. One of the drivers of air-to-ground collision is an unexpected battery depletion. And that is why we had a line of research on this that focused on using sensors that were mounted on the drone in terms of vibration sensors and thermal sensors, but also monitoring the battery parameters and the health of the battery so that we could predict, you know, the actual endurance of the battery itself. Because what we didn't want to face was, if we were taking a mission right up to say 5-6 minutes of battery endurance, that actually that would transpire that maybe it was 1 or 2 minutes in reality, and we could end up having a drone dropping into the sky. So that's why we put in that additional layer of risk mitigation. To summarize, those were effectively the 3 main pillars of the project: automating the data acquisition, the risk management, which considered air-to-air and air-to-ground collision in terms of collision with built environment, collision with uncooperative incursions, and the energy management side, which factored into both the endurance and the risk management. And that was the conclusion of the project in September of this year with the test that we saw, the videos taken in Hamburg. So that concludes our session. Thank you all for your time and thank you for coming. If there are any further questions or if you want to come and discuss, please do. Yeah, thank you. And I'll close out.